So hey everyone, welcome back to my channel. This is Lakshay here. So today we are gonna start with our lead code question number 216, which says combinational sum part 3. Before that we have also made videos on part 1 and part 2, and part 3 is also similar type. It's just a different variation of those questions. So let's see what this question says. It says find all valid combinations of k numbers that sum up to n such that the following conditions are true. Only numbers 1 through 9 are used. Second, each number is used at most once. Means each number should be used at most one, and the number should be between 1 to 9. Return a list of all positive valid combination. The list must not contain the same combination twice, and the combinations may be returned in any order. So let's see the first example here. Here we have given k equals to 3 and n equals to 7, which means we can make a combination of up to 3 integers, okay, whose sum will give us the result of 7. This question says this, this example says that. So what can be our combination? So 1 to 4. If we add this, these form give us 7, and also all the integers lie between the range of 0 to 9. Any other combination can be formed. Let's try any another 1, 3, 6. No, or any other between. You can make many number of combinations, so you can try any, but you will still get only one. That's why here is our output, only one. So how we can perform this question? Let's see how we can get this solution with the help of recursion tree. Okay, so let's see. Initially, let's take this example only. We have an empty string, means an empty. Let's clean it first. We got k equals to 3 and a target. Let's name it as target is 7. We have to create 7, and we have numbers till 1 to 9. Okay, so let's see, let's write them like this. So our index is currently at here. So at first step what we will get, we'll get r1, so we will add it in our combination, and our k reduces, so now our k is now reduced to 2. Okay, then again it calls this function, then another combination 1 2. Now our k reduced to 1. Then again it calls for the next index, that means 1 2 3, and now our case becomes 0. Now when you try to call another, it will check that if k is equals to 0, so it will check if k has reached 0 and a target is also has reached 0, because whenever we are adding an element, we are also subtracting from it to our with our target, like this. Our target was 7. When we added 1, it became 6. Then we added 2, so it becomes 4. Then we added 3, so it became 1. If our target has reached 0, that means that this subset will satisfy our condition, and it is having all the elements that will form our target value. But if it has reached negative, like this, if we have another element, let's see, like this one, we got 6, and we that took 3, it got us 3, but then we took 4 and it gave us -1. That means that we have taken large values like the 1 3 4, 1 3 4. It gave us what, 4 5 6 7 8, and our target was 7, so it was 1 greater. So that means if we got any negative value or our target has reached 0, then we return directly, because it's not satisfy our condition. But if our k becomes 0 and our target is also 0, that means it satisfies, and we add it to our final resultant vector. But this doesn't satisfy, so we return. That's why we also return from here. And when we return, so now we are at this condition where k is 1, so we are remaining one more chance. Then for another iteration, our I moves. So now we have used 3, now it tries for 4. 1 2 4. Then again it checks, does it again exceeds our limit, so it again returns. Then it again checks for 1 2 5. So it keeps on checking, but it doesn't get any or solution. But when it reaches here, we can see that it got our value. So whenever we get our value, it will directly add it to a resultant string like this, and then it returns. So when it returns like this, we are saved. Then it again checks. After all the checking, it will return from here. And now we have what? We have tried for 2. We can try for 3 also. 1 3. Then again here 1 3 4. 1 3 5. We can again check. Then again return from here. Then this is how we can ask for 9 times like this. Then we again tick 2 here 3, and it again form many combinations and again form, and keep on checking. Okay, so that's how our recursion tree look like. So let's write down the pseudocode to understand it more clearly how our function is actually working. So this is our main function. Okay, so but first of all we will create a vector result and a vector combinations, and then we will call our function. Let's suppose backtrack function, name it as backtrack. So first of all, what we will pass here, we will pass our k, that tells us that our vector should contains only k number of elements, and then our target, that is n, then our index, that is 1, because we want 1 to n numbers, not 0 to 9, because 0 don't have any value, so means it won't provide any value if we add it into our combination. That's why we start from 1, and then our combination and result, and at the end what we will return, as usual, our result, like this. Okay, so now this is only our main function, and now let's write down our backtrack function. It also takes same as k, and name the n as target, because this is what we want, and this is our index, and then our combination and resulted. Now what if was our first condition? If our k is 0, that means we have used all the elements, the size is now completed, and we can't add further elements, and our target is also 0. That means the numbers we have added till yet is their sum has reached to our target, means their sum is equal to our target. That simply means that this is our answer, and we push back that combination that we formed, and then we return. Okay, simple. But if that's not the case, then what we will check, that if k is reached 0 or target is smaller than 0, that means target has got to negative, that means our combination values is getting too much bigger. That also means that we return, but without adding that combination to our result. Okay, but if both these cases fails, means this is not the case, then it means that we are still able to add further values more. That's why we will start our loop for I equals to index till I is smaller than n, and we keep on adding. So what we will do, we will do combination dot pushback ri, and then we again call the function. And how we will pass our parameters, we will reduce our value k by 1, our target by I, because we have added the I already, and then again our index will pass the next index, because we don't want it to repeat, like 1 is calling again, it is adding 1, we don't want so we pass the next index, that is 2, so it will start from 2, like this. Then we pass our combination and result as same, and when it recurs back, we again pop it, so that our backtrack function will work properly. These are the main aspects of our backtrack function. So this is how our pseudocode looks like. This will help us form this tree and get our answer. So below here I will also provide you the perfect code. Here is pseudocode, but below is our code. Before that, you must try this code yourself. I think you can do it, and also try to dry run all the test cases. And this recursive tree is also very important, so you must try to create this tree by yourself, then this question will be more clearer to you. Now let's see our code. So it says same like we discussed, that this was our main function. It created a, here it named it as path, but we have named it as combination, means com, it means combination. Then again we pass a kn and our index as 1. As we discussed, we don't pass 0 because it has no value, so it will not contribute to our combination. Then we checked If it satisfies, it pushes, then we again check. If it doesn't satisfy, then we skips, and if satisfies, then we will simply return. Then our loop starts. Here we have did one wrong mistake, that our loop will run till 9. Okay, till 9. I have mistakenly taken n, but till 9 means all the values like 1 2 3 4 till 9. After that we are pushing our value, and we are pushing, and then we are popping again when it's this functions recurs back. Okay, so that is our cool code. Now let's discuss the time complexity. So the time complexity will be big O of 9 by k. Okay, and the space complexity will be big O of k. Why big O of k? Because we are using a stack data structure, and means we are not exactly using, but our recursion uses stack, and our max size can be k because k is the number of elements we can have in our combination. Here k was 3, so that's why we can only take 3 elements, that's why. And time complexity is big of 9 by k because the number of elements combination we can make is 1 to 9, that's why it's 9 by k something. So that's it. Thanks for watching. Stay tuned. Till then, see you soon. Bye bye.